Hello, welcome back. So, having discussed explicit and implicit methods and also consistency of these methods, there are still methods for parabolic PDEs. So, let us discuss one of the important methods. Of course, the title I kept it little not precise, because I have covered explicit and then implicit and then the definitions of convergence, stability and consistency, and we discussed definitely the stability aspects and then consistency of some methods. But still, since there are several uncovered topics, which still belong to parabolic PDE, I kept the title as just other numerical methods for parabolic PDEs. So, let us look at it. So, still we are considering the heat conduction equation. So, when I said this, it is understood that within a specific domain and then the corresponding initial and boundary conditions are given. So, now let us approximate this by forward time, but this one this at xi tj by average of values at j and j plus 1. So, this is a slight deviation. What we are doing? This we are going for forward, but whereas this at this point is approximated by average of values at jth level and j plus 1 level. So, accordingly we have this. So, now I am going for the average of. So, this is standard second order approximation central at j plus 1 plus this is again standard at j, second order approximation for central at j. So, the meaning of this is this. So, you can look at it, this is a usual forward, but here this is value of j plus 1 central for second order second derivative, and this is value at j. So, if you simplify this, we have with lambda equal to k by h square, the discretization simplifies to So, you can figure out all the terms at level j plus 1 we are writing to the left hand side, then all the terms at level j to the right hand side. So, this is called very popular Crank-Nicholson implicit scheme. So, this is implicit because at j plus 1 we have more than one point, more than one term involved. So, this is the implicit nature we have discussed before. So, this is very popular Crank-Nicholson implicit scheme. Okay. So, let us try with an example. Okay. So, the example we are considering, so the boundary conditions for all t, then we need initial conditions. Okay. So, this is of course for x boundary 0 to 1. Okay. Then further we need the parameters, say h is half, k is 1 by 4, this will give lambda equal to 1. So, first glance this sounds too much, because when the boundary is 0 to 1 we are going for h half. So, that means essentially you have only one grid point. So, suppose this is 1, so this is just half. So, this is only one grid point. Okay. However, along the time steps, so this is t j is 0 and j 1, and we can. So, let us see what happens for this case. Okay. So, u of 0 t equals to 0. Okay. So, this implies u of 0 j equals to 0, because this is x 0 is 0, x 1 is half, x 2 is 1. So, the boundaries. Okay. So, u 0 t is u 0 j is 0, then u 1 t is 0. So, the boundary is, this is the boundary. Okay. So, u 2 j is 0. Okay. Then the initial condition u of x 0 is x minus x square. Okay. So, this implies u I 0 is equal to x I minus x I square. Okay. So, accordingly the initial values at these grid points we can compute. U 0 0 is 0, u 1 0 is x 1 minus x 1 square. So, this is then u 2 0 is 0. Okay. So, now the discretized scheme, Crank-Nicholson scheme, is minus lambda is equal to okay. So, this we run at so since lambda is 1, so this goes off. So, let us consider j equals to 0. Okay. Then corresponding to I equals to 1 we have. So, please j is 0, I is 1 and lambda is 1 we have. Okay. So, lambda is 1 we have it from for the choice we have taken. Okay. So, now this implies minus u 0 1 plus 4 u 1 1 minus u 2 1 is u 0 0 plus lambda is 1, this term goes off, u 2 0. However, please observe carefully, 0 j is 0, therefore, this term is 0, okay. This is 0 and 2 0 is 0, okay, right. Then 2 1, okay, 2 1 because of by virtue of this. So, this implies the only unknown is 0. Okay. Suppose we run for j equal to 1, this implies okay. Suppose if we do this, even now this is 0, this is 0, this is 0, this is 0 because by virtue of this. So, we are getting okay. So, what could be the reason? So, if you proceed all the, so this is u 1 2. So, if you proceed along the time stepping, we may end up with getting 0 values. So, the reason is the choice of our step size, so that is too much. Okay. So, better to have go for finer grid. So, this could be the lesson. Okay. So, accordingly let us choose h is 1 by 4, k is 1 by 6. Of course, still for simplicity the grid parameter is 1. Okay. So, now in this case if we run the equation, okay, this gives equal to, I mean I am putting the simplified version, and u 2 0 we have computed to be 0. Okay. In this case we have to compute again. Okay. So, in the earlier case it is 0. So, u 2 0 we do not have. Okay. So, now if you go for I equals to 2, of course, j remain the same, then we have minus u 1 1 plus 4 u 2 1 minus u 3 1 equal to u 3 0 plus u 1 0. Then I equals to, so h is 1 by 4. So, let us see what is happening in this case. X 0 is 0, x 1 is 1 by 4, x 2 is half, x 3 is 3 by 4, x 4 is 1. So, how many unknowns we expect? So, 3 unknowns, and what are they? So, u 1 1, u 2 1, u 3 1. Okay. So, these are the unknowns. So, in this the unknowns are so, since Crank-Nicholson is explicit, we expect system of equations. So, similarly, okay. So, now for I equals to 3, we get okay. So, here again, so these are there are repetitions. So, if we tick only one time, so 1, 2, 3. So, this is repeated, 2 1 is repeated, okay. 1 1 is repeated, 3 1 is repeated. So, we have 3 equations and 3 unknowns. Solve for okay. So, this is an explicit, this is an implicit, sorry, this is an implicit again one step method, because to compute the values at a higher level you need only the past data at one level, okay, the immediate one before. Okay. So, since it is an implicit, it is a concern to solve the system. This is very simplest. So, we could get the solution, but in general if you have a larger system, how do we go about it? Okay. So, let us see, we rearranging the terms of the finite difference scheme, we get so, it is slightly boring, but this gives some idea. So, I minus 1 j plus 1, I plus 1 j plus 1, I minus 1 j, I j, I plus 1 j. Okay. So, this is the grouping. Further, this can be written as u. So, I will bring up only the terms at j plus 1 plus C I j, where C I j is this term plus lambda by 2 times whatever missing in this, but written here. So, they will be I minus 1 j, I j. Okay. So, this is just for convenience. So, then accordingly we have u I j plus 1 is lambda by, because we have 1 plus lambda there. Okay. So, this can be put it as a system. Okay. So, the system has been rearranged in this form. If you observe closely, we are looking for I at j plus 1 level. Okay. The value at x I j plus 1 level, and right side you have j plus 1 terms, 2 more, and this entire C I j contain only terms at jth level. Okay. So, now this we can solve using any iterative method. So, for example, we define Jacobi iteration. So, u I, so we can keep it j plus 1, now we can drop. So, this is the index for iteration. So, that means given the values at jth, latest is used to compute at the next level, okay, next iteration with respect to n. So, that means even at j plus 1 time level, whatever available you have at the previous iteration, we use them, and we this is standard Jacobi iteration. Then Gauss-Seidel. So, in this case, whatever is available we are going to use. Okay. Up to that level of iteration. So, you see u I minus 1, u I plus 1, if you have at n plus 1th iteration, we use them to compute I. Okay. So, the Gauss-Seidel, and of course, the other one successive over relaxation. Okay. So, this is another standard method to solve system of equations. Okay. So, this is successive over relaxation. So, this is the relaxation parameter. So, you may refer numerical solutions to PDE, G.D. Smith. Okay. So, you get a better idea. Okay. So, this is for any system of equations. Okay. So, so far the explicit and implicit methods we have discussed, including the Crank-Nicholson, they involve the values at 2 time levels. That means, if you give at the past time level, we can compute at the next time level. Okay. So, now let us see an example of a method where you have more than 2 time levels are involved. Okay. Of course, it depends on the way we discretize. Okay. So, 3 level difference method. Okay. So, still we are with our heat conduction, then use central. So, first term we are deviating. So, then this is standard central for second order. So, accordingly we have see for the first order time we are using central. So, this should be 2k. So, this is k square and h square this one. Okay. So, this we are going to simplify this is equal to u I j minus 1 plus k by h square is lambda, hence 2 lambda okay. So, this is Richardson's method. So, when we say 3 level j plus 1, j minus 1 and j. Okay. So, we will see maybe in some tutorial try to solve problem using this. Otherwise, the important observation is the discretization here is bringing one more time level. You can see, had it been forward or backward, we would have used j minus 1 or j plus 1 j, but because of this central we get j plus 1, j minus 1 and then right hand side you have j. Okay. So, this is an observation. Then let us see one more Dufault-Frankel. So, these are the standard names in literature. Okay. So, now what we do in Richardson's method, if we replace u I j by the average. Okay. So, if we do that we get okay. So, then rearranging okay. So, what is happening in this case? So, this is say I and this is j, j minus 1, j plus 1, I minus 1, I plus 1. Okay. Now, j plus I, j plus 1. So, this point, okay. Then right hand side I j minus 1. So, I j minus 1. So, this point is involved. then I minus 1 j, then I plus 1 j. Okay. So, it is implicit, this is explicit, but however, you can see you need values at 2 values at jth level and 1 value at j minus 1 level. Okay. So, it is explicit, but however, it is demanding values at 2 time levels. Okay. So, to that extent it is explicit. Okay. So, you can see how we march past, because if you want the value here, it expects this, this and this. Okay. So, we have to march past like that. So, these are some of the variations which are standard in literature. Okay. However, if I keep on talking about the error expansions by routine calculation, which we have done for at least explicit and one implicit method, then you get bored. So, in order to discuss about the error and then stability of these methods, maybe we shall wait until we learn one more technique to discuss stability other than what we have learnt. Okay. So, then we can come back to these methods and discuss under what conditions these methods are stable, how far these are comparable, including the Crank-Nicholson method, because when I mentioned Crank-Nicholson method is important. Yes, it is really important, because many of the problems in fluid mechanics etcetera, people use a Crank-Nicholson method. Okay. So, we have postponed the discussion on the stability of these methods, okay, until we learn more rigorous analysis of stability. Okay. So, before we go to that, see whatever problems we have discussed so far, the boundary conditions are just the function values are prescribed. Okay. So, only the function values are prescribed on the boundary. In case if this is replaced by kind of derivative boundary conditions, then what is going to happen, because it is a concern. Okay. So, because there is a big difference when derivatives are given on the boundary, what would happen? You do not have explicit function value on the boundary. So, that value also becomes another unknown for us. Okay. So, this is going to be slightly interesting. So, let us proceed to derivative boundary condition. Okay. So, derivative boundary conditions. So, let us start with an example, because even if we take a general case, this is going to be little kind of hand waving. So, better to discuss this with reference to an example. So, consider okay, then initial condition u of x 0 is 1, okay. Then boundary condition dou u by dou x at okay. So, there is a big difference, you have to observe this initial condition. Of course, this is non-homogeneous, it is not 0 here, you have a non-zero quantity. Further, instead of the function value, you have derivatives prescribed on the boundary, both at x equal to 0 and x equal to 1. So, let us say for this problem h is 0.2 and lambda is 1 by 4. So, accordingly we compute a k. So, you assume that we are solving for that time step. Okay. So, now if you use, as far as the discretization of this is concerned, you can discretize either with explicit scheme or implicit scheme. However, there will be a deviation when we discretize the corresponding boundary conditions compared to the earlier case of function value prescribed on the boundary. Okay. So, let us see how this deviation will play a role. Okay. So, consider explicit scheme. Okay. So, we have considered this explicit scheme. Now, call this 1. Okay. Now, we have to discretize the initial conditions. So, initial conditions if you discretize, I am sorry, this is 1. So, this implies u I 0 equals to 1. Okay. So, call this 2. Now, consider the boundary conditions. Du by dx equals to u at x equals to 0 for all t. So, this was the condition, we have one of the conditions at x equal to 0. Now, if you look at the grid, x 0 is 0, x 1 is 0.2, x 2 is 0.4, x 3 is 0.6, x 4 is 0.8, x 5 is 1. Okay. Now, what is going to happen here? If you look at this and then discretize, this is the derivative with respect to x. Okay. So, now at the boundaries there is a big concern whether to use forward or backward or central. Okay. It is standard practice to use central. Okay. So, there one can justify that. So, if we use, we are going to get u I plus 1 j 2 h equals to u I j. Okay. Now, this value this is at x equal to 0. So, that means at I equals to 0. So, at x equals to 0, I is 0, this implies u 1 j minus u minus 1 j is equal to 2 h u 0 j. Okay. So, an important observation, when we have this line, this is going to be x minus 1. Similarly, this is going to be x 6 and x minus 1, x 6 both are outside the domain. However, this quantity appears in our equation. Okay. So, since this is outside our domain, we call this fictitious value. Okay, we have to handle this very differently. Okay. So, how do we handle? Put down explicitly is equal to u1j minus 2h u0j. Okay. So, called 3. So, we have a fictitious value getting introduced because of the discretization of the boundary condition, derivative boundary condition at the boundary, at one of the boundaries. So, that fictitious value we have written explicitly. Okay. Now, let us do it for the other end as well. We have at x equals to 1 for all t, dou u by dou x equals to u. This is another boundary condition. So, now u I plus 1 j so this is a general discretization. Then at x equals to 1 I is, so let us have the grid because we need it. So, this is 0, 0.2, 0.4, 0.6, 0.8 and 1. So, this is I is 0, 1, 2, 3, 4, 5. So, at x equals to 1 I is 5. So, now if you put that, we are going to get u 6 j minus u 4 j by 2 h equals to u 5 j. Okay. So, now the boundary condition which I have defined at 1, this is minus sign here. So, accordingly if we consider this minus sign, we get a minus sign here. Okay. So, that was a slip because I have the worked out example for this case. Okay. So, now as I discussed, this corresponds to, this is supposed to be 1.2 for I 6, but this is outside the domain. So, that is a fictitious value as well. Okay. So, therefore, we write down u 6 j is equals to u 4 j minus 2 h 5 j. Okay. So, to brief it, we have the following. We have one, the explicit scheme which we are supposed to run at the grid points, and we have the initial condition, then we have one boundary condition we have discretized, and as a result we got a fictitious value, and we have expressed this in terms of another additional equation. Then another boundary condition which we have discretized, we got another fictitious value and we have expressed in terms of another equation. So, let us summarize these equations. Okay. So, we have u I j plus 1 Okay. Where this is valid, I will get back to you in a moment. So, then we have u minus 1 j then we have u 6 j okay. Of course, we have the initial condition. Okay. Now, in order to decide where this is valid, 0, 0.2, 0.4, 0.6, 0.8, 1. Okay. Recall the earlier cases where we have the boundary data explicitly in terms of the function value. So, then the values along the boundary are known to us. Okay. The values along the boundary are known to us at every time step. Okay. However, in this case, because of the derivative boundary condition, we do not know. So, let us say the time stepping corresponding to the time stepping. Okay. So, in the earlier case, when the function values are given explicitly, so I will give an example. So, the function values are given explicitly, okay, let us say, then these are known. Similarly, these are known. So, the unknowns are in this case unknowns. So, what is this case? This case is when the function values are given at the boundary. Okay. But what is this case? Derivatives are given at the boundary. So, in this case the unknowns all of them are going to be the unknowns, because in this case we know these, okay, but in this case since the derivative is given, we do not know the value here, we have to determine. So, for the present example 1, 2, 3, 4, 5, 6. So, there are 6 unknowns, right. So, now how many equations we have? If you look at it, in some sense you have 4 equations, right. So, we need 2 more equations, okay. We need 2 more equations. How we are going to get? In the earlier case, the discretized equation we were running for I equals to 1, 2, 3, 4, okay. But we were not running for I equals to 0 and I equals to n, okay. But in this case the derivative boundary condition introduced fictitious values which are outside. So, this is x minus 1. So, corresponding fictitious value, and in this case x 6 and the corresponding fictitious value. So, if you run this equation for I equals to 0 as well as 5. So, let us see what happens if you run for I equals to 0, yeah, there we are going to get u minus 1, and if you run for I equals to 5, we are going to get u 6. So, that means 2 more additional equations we are going to get. Okay. So, that may resolve the issue. So, let us try to do that. Okay. So, note in order to eliminate fictitious values u minus 1 j and u 6 j, okay, run the equation 1 at I equals to 0 and I equals to 5. So, if we do that, okay, then similarly I am sorry, this is lambda u 6 j. Okay. So, we have the fictitious value here, we have the fictitious value here, then we had minus and u 6 j equals to u 4 j. So, we can eliminate these two fictitious values. Okay. So, when we eliminate, we get, by eliminating we get, so this is the original equation which we have discretized and obtained, which is still valid at 1, 2, 3, 4. Then we have eliminated the fictitious values, okay. So, this is all the unknowns. So, I am making it shorter 0, 1, 2, 3, 4, 5. Okay. So, at these values we can compute. So, this is for 1, 2, 3, 4, and this is for 0 and this is for 5, and you can see there is no fictitious value. So, 4 equations here, this is one equation, this is one equation. So, total 6 equations and 6 unknowns. Okay. So, we can compute for the current case, we can compute so this is going to be some value and this u I j plus 1 and u 5 j plus 1. So, we can compute by considering j equals to 0 and I 1, 2, 3, 4 solve. Okay. So, the main idea in this is the derivatives, when you discretize they get additional terms both to the left and to the right, and these are called fictitious terms, and in order to eliminate them what we do, we run the discretized equation at the end points as well, which was not the case when the function values are prescribed. So, when we run at the end points, the fictitious values are introduced in the equation and we eliminate these fictitious values across and we obtain a consistent system. Okay. So, maybe the tutorial we see exactly how problems on this can be solved. Thank you.